So, good afternoon to all. I think it's lunchtime, so it's dwindling population. Anyway, today I'll be talking about holographic tensor models based on the work I did with Chetan and Sambuddha from ICTS, and also on the work that Chetan, Pawan, and Sambuddha did on a follow-up paper. So, this is an overview of the talk. I'll just introduce why we start with introduction on like SYK, and then move on to Gurau-Witten models, which is one of the first tensor models to come on this topic, followed by Klebanov-Tarnopolosky model, which also it's slightly different from the Gurau-Witten model, as we'll see. I'll also talk about the random matrix classification that was introduced by Andreev-Altland-Zirnbauer, and discuss some results on the numerical case for the Gurau-Witten and this Klebanov-Tarnopolosky models. So, what exactly is the SYK model? SYK model, the Hamilton is given by Q Majorana fermions coupled by the coupling is drawn from Gaussian ensemble, with the mean being 0 and the sigma normalized in such form. So, what exactly is done is that like you take an ensemble of j, ij, I1, I2, I3, etc., and you average over them, and that essentially is what gives you the random behavior. So there are three striking features that SYK model has, which has been discussed over length over the last year with like hundreds of papers. The major one is that it's solvable in large N. It has been shown to be maximally chaotic, which saturates the Maldacena-Stanford bound, and there is an emergent conformal symmetry in the IR limit. So now we'll move on to the Gurau-Witten model. So Gurau has been discussing this bosonic tensor models for a long time by now, and Witten identified a fermionic color tensor model late last year, and the is given in this form. So I'll expand on what exactly this psi 0, etc., contraction looks like. So to point out, J is a real coupling, and the N is it comes from the gauge group, which I'll come to in a moment, and it's chosen in such a way that like you have a nice scaling limit in the large N. Like real fermionic wheels, and A is taken from 0 to D, and these indicate the colors. And each of the psi A's transform under a real irreducible representation of a gauge group. So what exactly is the gauge group? The gauge group is constructed out of pairs of psi A, psi B's in this way. For a unordered pair AB, where A is not equal to B, we associate a gauge group GAB, which in this case we take to be ON, and this full symmetry group is given by the product of, this is a small typo here, it's GAB, which will be a ON to the power D into D plus 1 by 2. There will be an overall discrete symmetry corresponding to some of the flips that you can do in the size. So since you can see that so here if you look at it, psi 0 and psi 1 can be identified to have a gauge group, transform under a gauge group of G01. And like psi 0 will transform under G02 with respect to the next psi 2, and etc., etc. So each fermionic field can be associated with indices corresponding to these gauge groups, which can be written as IA0, IA1, etc., up to IAD, but the IAA index is dropped. I'll come to an explicit construction for the case of 2 and 4, where I think this construction will become more explicit. So also one can see from here directly that there will be D indices, gauge indices for the group indices, D of them will be there. And given the fact that we are taking ON, and to be precise, we take IABs to be transforming as a vector under the group GAB. So each of these indices run from 1 to N. So each psi has n to the power d components, and we have d plus 1 colors. So that essentially gives you d plus 1 times n to the power d real components in the theory, which we take to be the large N, and this n is what is taken to be relevant for large N once we are comparing it to SYK. So the simplest case one can look at is d equals 1. So there are only two cases, psi0 and psi1. And there is only one gauge group that we have to associate with it, which is G01. And G10 is G01 because we are looking at unordered pairs of A and B. So the Hamiltonian is directly given by psi0, psi1. And there is a vector index on psi0 and psi1 associated with this G01. This theory is a free theory and is trivial for any value of n that one can look at. So now we'll come to the case d equals 3, which is the one we considered in our paper. So here, if you look at it, this is an easy way to picture how exactly this construction is happening. So these are the color indices of 1, 2, 3, and 4. And so there is a group G01 associated for 0 and 1, 0, 2, and 0, 3, and similarly for all of these. Yeah, this is actually like the famous vertex, but this can also be easily used to see the.
I'm just saying, you usually use colored coding for the various.
Yeah.
You're not using.
No. So from this, you can see that like the 0, 1, there will be an I that is contracted, 0, 2, there will be a J that is contracted, and 0, 3, there's a K that's contracted, and like the following indices are also contracted in a similar way, and you obtain this Hamiltonian. So also, these psi's are Majorana fermions, so they have the canonical anti-commutation relations given by this, which essentially helps you in writing down a representation for this in terms of Euclidean gamma matrices of SON or SOD plus 1 times n to the power d. This will come in handy once we are trying to construct or trying to numerically diagonalize the entire d equals 3 model later. So one can now look at the Klebanov-Tarnopolosky model, which was introduced slightly later after Witten. Here, what exactly happens is the color indices are dropped out, and there are d indices again for each of the psi's. So they are identical psi's, and each index, takes the values 1 to n, and the total degrees of freedom are given by n to the power d. And the symmetry group of the theory is On to the power d. So in order to construct contractions that are gauge invariant to write the Hamiltonian, we need at least d plus 1 terms. And the Hamiltonian here for this case is given by this one, where this is essentially the same as the Hamiltonian we wrote here, except for the color indices have been dropped. The reason why one writes this way is that it produces the right melonic structures once you're looking at large n cases. So now we'll look at why tensor models are interesting. So tensor models are truly unitary quantum mechanical systems, in the sense that you're not at any point doing any disorder average or stuff like that. So you're really working with a quantum mechanical system. And while the disorder averaging is being avoided, the large and melonic structure of the theory of SYK is preserved. And all these models have been shown to saturate the Maldacena-Shankar-Stanford chaos bound. So now I'll just briefly review the Andreev-Altland-Zirnbauer classification. So the SYK model has, in the paper by Kotler and company, they analyzed n for the numerical diagonalizations for n starting from 18 to 34, and classified the ensembles as belonging to the Gaussian unitary ensemble, Gaussian symplectic, and the Gaussian orthogonal ensemble. So this essentially belongs to a threefold classification in the Wigner-Dyson ensembles. And there's a larger classification due to Andreev-Altland-Zirnbauer, who have classified the quantum matrix theories into a tenfold classification. The classification is based on discrete symmetries. So the two symmetries that you look for, one is the spectral mirror symmetry. Spectral mirror symmetry is that if the Hamiltonian has an eigenvalue, then if let's say E0 plus E, then E0 minus E is also an eigenvalue, E0 being some mid-level value. So you have like around the point E0, you have a symmetry in the values of the eigenvalue.
For some special reason.
Yeah. So if you E0 is the mid-level of all of this. It's at the center of all the eigenvalues. So this condition essentially requires that the Hamiltonian anti-commutes with such an operator S. We can also associate a time reversal operator. T is an anti-unitary operator which commutes with the Hamiltonian. So this is the full tenfold classification. So you're classifying based on what are the symmetries that are available to your Hamiltonian. So if you look at, there is the fact that there is only spectral mirror symmetry, but you don't have any time reversal symmetry. Then there are three classes. For Hamiltonians that are symmetric under both S and T, you have four possibilities coming from the S square taking plus minus ones and T square taking plus minus ones. And for Hamiltonians that have only time reversal symmetry, there's T square equals plus 1 or minus 1. And if there is no symmetry at all, it belongs to class A, which is the Gaussian unitary ensemble. And this only time reversal is the orthogonal and symplectic ensembles, the Gaussian series. So what they found for the SYK case was the ensembles belong to any of these three. Although T square is not like an exact symmetry of the Hamiltonian, it's like an effective one that is gotten after the disorder averaging is performed. So yeah, we'll come to the gamma matrix assignments now. Here I'll be talking about the gamma matrices assignments we did for the Gurau-Witten case. So just to recap, the fermions can be realized as Euclidean gamma matrices of SON or SO d plus 1 times n to the power d. So we'll be looking at the, so as I said, d equals 1 is a very trivial case for all and it is exactly solvable. So the next one to look at will be d equals 3 and the easiest case will be n equals 2, which is the first non-trivial case. So here what we'll be requiring is SO32 gamma matrices. So the SO32 gamma matrices, we can find a representation that is real and symmetric, in the sense that like you have you can construct 8-dimensional real symmetric representations for gamma matrices, and you can successively use them iteratively to construct the n equals 32 gamma matrices which are real and symmetric. So and then for each of the psi a ij case, you assign the gamma matrices in this form. Yes, this is for the Gurau-Witten case, yes. Using this, we can do the contractions which was there in the Hamiltonian explicitly, which means there will be like a sum of products of 4 gammas, and we can write down the full Hamiltonian as a matrix from. So the SO32 gamma matrices are 65,536 square matrices, and this already was maxing out our computational powers that that was available to us, and from various discussions or various comments that we have found, this or like slightly bigger than these are the matrices that are like maximally diagonalizable in computation. So if you so one thing that really helped in the Gurau-Witten case is that we found that the Hamiltonian was indeed sparse in the sense you can see. So what exactly, this is a matrix plot of the Gurau-Witten Hamiltonian. So each of the black dot is essentially a +1 or a -1, and the left out spaces are zeros. So you can see that there's a lot of zeros that are there in the Hamiltonian, which essentially says how sparse the matrix is. So this one is like really sparse. When I come to this KT model, I'll give something more, because there is essentially the sparsity has become, the sparsity is 10 times as less as that you can find in the, yes. Yeah, so for SYK models, like every psi ijkl is supplemented with a, JIJKL, and like it's a very dense matrix that one can have. We have a plot of that paper. Nobody is interested. So from this, we can explicitly diagonalize the Hamiltonian and find out all the set of eigenvalues. And we find that the eigenvalue spectrum is symmetric about E equals 0, which means you have like a spectral mirror symmetry. And the ground state is unique with no degeneracy. The ground state meaning I'm looking at the smallest eigenvalue, the negative most eigenvalue. And there is a huge degeneracy at E equals 0. So this is a density of states plot. You can see that like it is symmetric around the E equals 0 axis to either side, and at E equals 0 you have like a large number of states that are lying there. So one can find the integrated density of states plot like using a summing over the binning.
By saying that there is a huge degeneracy around T equals 0, I mean
at T equals 0, so there's a large at T equals 0, not around. Sorry, it's at T equals 0. You have like a large number of states.
No, about the ground. E equals 0.
Yes, the ground state is unique in the sense that it's the small state. Yes. So from this you can also find the integrated density of states. And again, the jump here is caused by the fact that there is a huge degeneracy at the energy level E equals 0. So then we looked at the spectral form factor, which has been discussed in Kotler et al. As a good diagnostic for looking at random matrix behavior of the case. We compute the same quantity. So here what it is said beta t is the trace over e to the minus b plus it, and you're plotting for t at some temperature beta. So this purple line is the spectral form factor one obtains by just plotting this directly. So in the SYK case, what they were doing was they were doing a disorder averaging over a large number of ensembles, which smoothened out this plot eventually. Here we don't have the crutch of like doing an ensemble average. So what we can do is a sliding time average, and the green and the black plot are time averages done for various different time windows that one can take.
Black one lost the treatment of that.
Yes, but it yes. But the fact is also that it plateaus out at late times. It's also log plot. And here this is, oh sorry, it went down below. So this is the beta equals 0 case, and this is the beta equals 0.5 case. So you can see that at both cases there is a plateau that is forming at late times. Just remind this are log plots. So in the SYK case, when Kotler et al. Were discussing it, they were the fact that you can form a plateau is essentially related to the idea that there are no near degeneracies around any eigenvalue, in the sense that you will have some the concept of level repulsion. So what exactly is level repulsion? So to see whether the spectrum has level repulsion, we unfold the spectrum, which is a standard process. There's an algorithm, and you can plot the integrated density of plots after density of states after the degeneracies have been removed, and the unfolded level spacing. So if you look at it here, the probability of finding a level at a distance s from any eigenvalue actually goes up and comes down, which essentially means that there are no real close degeneracies that you can find. An integrable system, for example, will find you will find that it will be a Poisson distribution, which means it will be something like this. The fact that there is a turnaround is a major indication that the system has level repulsion and thereby random matrix behavior. So as we can see that the spectrum clearly has a mirror symmetry, and we can explicitly construct the mirror symmetry operator. The operator S is unitary and it squares to 1. We can also find a time reversal operator. It's slightly more complicated to write down. And thus, and we find that the T also squares to 1. Thus, it identifies to the BD1 class of the Altland-Zirnbauer Andreev classification. The next simplest Gurau-Witten case will be D equals 3, N equals 3, which will correspond to finding gamma matrices of dimension of SO 108. And or if you're looking at D equals 5, N equals 2, you'll have to find gamma matrices for SO 190, which will be like preposterous matrices, which I don't think is possible to diagonalize. So they are computationally inaccessible unless we have like some other clever way of splitting.
So why are you doing GW and not KT?
KT has been done by Chetan, Pawan, and I'm coming to the results of that. So you can split it into levels and you can possibly diagonalize part by part. So now I'll just mention the results for the Klebanov-Tarnopolosky model. So here there are 3 tractable cases. First one is D equals 3, N equals 2. So D equals 5, N equals 2, and D equals 3, N equals 3. So D equals 3, N equals 2 corresponds to N equals 8, or it doesn't have enough eigenvalues to indicate any chaotic behavior. So the fact is that like here also, since you have like anti-commutation rules for the psi ijk, you can again map it to
16, 2 to the power 4, 2 cubes.
Yeah, 2. It's n to the power. So then the next case was D equals 5, N equals 2, so the n will be 32. But as I said just before,
it's not the indicating chaos, it doesn't have chaos. Like D equals 3, N equals 2.
Yeah. So yeah, this case doesn't have chaos. It's
qualitatively different.
so D equals 5, N equals 2, the corresponds to N equals 32, which is again finding SO32 matrices, but the Hamiltonian creates too many more terms that the matrix becomes too dense to be diagonalized. And the other tractable case is the D equals 3, N equals 3, where you have to find gamma matrices corresponding to SO27. So this was done by them, and the eigenvalue spectrum looks like this, which is qualitatively similar to what we find in the Gurau-Witten case. So you can write down the density of plots, you can plot this density of states plot and integrated density of states plot. And you can also look at the spectral form factors. Here also the red one is the untime average spectral form factor that one computes directly for beta equals 0 and beta equals 0.5, and these are various time averages that sliding time averages that have been done. You can also remove the degeneracies and unfold the spectrum and look for level repulsion, which indeed it shows. So some comments: the uncolored tensor models have features as that of SYK at finite, which means that like we have been able to find that it plateaus out in the tractable cases that we have. The Hamiltonians of tensor models belong to one of the ensembles of the IISc classification. A full classification of all possible NND has been done in the paper by Chetan and Pawan, etc. And within the numerical cases, tractable cases of the tensor models, one can see indications of chaotic behavior similar to SYK.
There is no chaos?
No, there is chaos in the sense here the main factor is that like you can find that it plateaus out, and plateauing out is a result of the fact that like you have level repulsion.
Right.
So,
But you said the earlier.
so there's the yeah. This is like a trivial case. Yeah. So this 4 plots have been discussed for the D equals 3, N equals 3 case.